Good evening, everyone. Today, I will be sharing my lecture on halogen derivative. It is under A-level chemistry, organic chemistry. So this is the content of today's lesson. We will talk about halogenal alkanes, their properties, both physical and chemical. In terms of chemical reactions, halogenal alkanes undergo nucleophilic substitution as well as elimination. We will also talk about the relative strength of the carbon to halogen bond and discuss the unreactivity of halogenal arenes. So these are the learning outcomes under the A-level syllabus. This is the lecture outline. It is a very long lesson, and here are the references. Now, introduction. Halogen derivatives are halogen-containing organic compounds. Their molecules contain the CX bond, where X is one of the halogen in group 17. Halogen alkanes or alkyne halides are halogen derivative of alkanes, where one or more hydrogen atoms of the alkane molecules are replaced by a halogen atom. Halogen arenes or arene halides are halogen derivative of arenes, where one or more hydrogen atoms of the benzene ring in the arene molecules are replaced by a halogen atom. The halogen atom is bonded directly to the benzene ring. So these are the structures of halogen alkanes, halogenal arene, their general formula, and the examples. This is a short summary of the various examples of halogen derivative and their use. Halogen alkanes are denoted by Rx, where R is alkyne group or a substituted alkyne group, where X is F, Cl, Br, or I. This is the general formula for mono-substituted saturated halogenal alkanes. Mono means one. One hydrogen atom substituted with a halogen. Every halogenal alkane has at least one halogen atom bonded to a sp3 hybridized carbon atom. The carbon-halogen bond is a halogenal alkane is polar because the halogen atom is more electronegative than the carbon atom, which explains why carbon or the alpha carbon here is of a partial positive charge, while the more electronegative halogen is of a partial negative charge. There is a net dipole moment, making the molecule polar. Halogenal alkanes are named as derivative of the corresponding alkanes. The position of the halogen atom is indicated by the numbering of the carbon atom to the chain to which it is attached. For example, chloroethane, 1,3-dibromopropane, where the two bromine atoms are attached to the first and the third carbon atoms in the molecule. 2-bromobutane, where the bromine is attached to the second carbon in the longest continuous carbon chain. 4-iodopentuene, the double bond between carbon is between the second and the third carbon, and the iodine is attached to the fourth carbon in the carbon chain. As for cyclic structure, we have the bromocyclopentane, and for arene, we have chloromethylbenzene as the example, which is an aromatic compound. Halogenal alkanes can be classified as primary, secondary, or tertiary, depending on the number of alkyne or array groups that attach to the carbon atom bonded to the halogen, which is known as the alpha carbon. In general, the alpha carbon is the carbon atom which the functional group is bonded to. Primary halogenal alkanes have one alkyne groups attached to the alpha carbon and two hydrogen atoms attached to this alpha carbon. Secondary halogenal alkanes has two alkyne groups attached to the alpha carbon, while tertiary halogenal alkanes have three alkyne groups attached to the alpha carbon. And there is no hydrogen atom bonded to the C directly. Halogenal alkanes are polar compounds as mentioned. The dipoles couldn't cancel off each other, making the molecule polar. So, two types of intermolecular forces exist between the molecules. Permanent dipole forces known as PDPD, instantaneous dipole-induced dipole forces, IDID. So, at room temperature, they exist as gases and liquids. The boiling point of halogenal alkane is higher than the corresponding alkane because for halogenal alkanes, there exist PDPD and IDID attractive forces, whereas for the alkanes, only IDID forces exist. For halogenal alkanes with the same halogen, with the same number of carbon, the boiling point increases as the number of carbon atoms increase, or X is the halogen. So with the same number of halogen, the boiling point increases as the size of the carbon chain increases. So as the size of R increases, the number of electrons per molecule increases. The size of electron cloud increases, resulting in greater ease of polarization of electron cloud. This increases the strength of IDID, not PDPD. For halogenal alkanes with the same number of carbon chain, the boiling point increases as the size of the halogen increases. The reason is the same as above. Although halogenal alkanes are polar, polar molecules may not be soluble in water. This is because they do not form interaction with water molecules via hydrogen bonding. In fact, they are soluble in organic solvents because they are able to interact with solvent molecules via IDID attractive forces. Fluoroalkanes is less dense than water. Monochloroalkanes likewise. They are also less dense than water. As for chloroalkanes with two or more chlorine atoms and bromoalkanes, iodoalkanes, they are denser than water. Now, halogenal alkanes may be prepared in the lab from either alkenes, or alcohol. So this is the general outline of the preparation method. Starting from alkanes, we can use free radical substitution to react alkanes with a suitable halogen, chlorine or bromine under UV light. However, this is not a good method because poly substitution can occur, leading to a mixture of products. Hence, the yield of the desired product will be low. The use of a limited amount of the halogen will help to minimize poly substitution. Preparation of halogenal alkanes with only one halogen atom per molecule. So in this case, we use HX, where X represents the halogen. So we can use dry gaseous hydrogen halide at room temperature to avoid free radical substitution. The mechanism for the reaction is electrophilic addition. If the alkene is asymmetrical, the major product is predicted by Markovnikov rule. But when propene reacts with HBr, the major product will be as such. To prepare halogenal alkanes with 2 halogen atoms per molecule, we use halogen dissolved in CCl4. Carbon tetrachloride at room temperature, again, to avoid free radical substitution. Free radical substitution can also occur with high temperature and not just at UV light presence. So the mechanism for this reaction is also electrophilic addition, where we are to produce 2 halogen atoms in this case. Alcohol can undergo nucleophilic substitution reactions in which the OH group in the alcohol is replaced or substituted by a halogen atom X. This reaction involves the cleavage of the CO bond and the formation of CX bond. The reagents and conditions are as such. We either use dry HX with heat, PX3, PCl5, SOCl2 without additional heating in this case. Now, the first method involves the use of hydrogen chloride and heat. If a solution of hydrogen chloride is needed, it should be concentrated and not dilute. The heating is necessary to break the stronger CO bond in the alcohol. So, looking at this example, we have ROH plus HCl heating. There is a replacement of the OH by the Cl in the molecule. So this is one of the example. CH3CH2OH ethanol reacts with hydrogen chloride. The use of concentrated acid and zinc chloride with heating. Note, for the reaction involving primary or secondary alcohol and HCl, we use zinc chloride as the Lewis acid to promote the reaction. The zinc chloride coordinates with the oxygen in the alcohol the same way a proton does, except zinc chloride coordinates more strongly. As for tertiary alcohol, they react more readily with HCl. The alcohol can just simply be shaken with concentrated HCl at room temperature without heating to produce the halogen alkane. With hydrogen bromide and heat, ROH plus HBr heating produce RBr and water. So in this case, the HBr is generated in situ from the reaction between concentrated H2SO4 and KBr. So HBr was formed and the HBr reacts with the alcohol to form RBr directly. Heating is necessary. As for the reaction of hydrogen iodide with alcohol, The HI is generated in situ from the reaction between concentrated phosphoric acid and Ki. So when Ki reacts with phosphoric acid, HI is produced, which reacts with the ROH. So in this case, we do not use concentrated sulfuric acid if you want to add iodine to the molecule, because concentrated sulfuric acid is an oxidizing agent that could oxidize HI to I2, such that there's effectively very little or no HI available for subsequent reaction. Other methods include use of phosphorus trihalides, PX3. X can be any halogen. So simply just react the alcohol with PX3 to obtain RX and H3PO4. All right. So PI3 alone is not sufficiently stable to be stored. So it has to be generated in situ during the reaction itself by the reaction of red phosphorus with iodine. And the condition must be anhydrous, because if there's water available, it will react with pH3. So these are the examples of reactions involving phosphorus trihalides to prepare our halogenal alkanes. We can also use PCl5 phosphorus pentachloride at room temperature, where the solid state of it will react with alcohol to produce the steamy acidic hydrogen chloride film. So this reaction can occur at room temperature and happen quite rapidly even at room temperature. And the condition must be anhydrous to prevent the reaction between PCl5 and water. So this reaction can be used to test for the alcoholic OH group by testing for the steamy acidic hydrogen chloride film. So this preparation can be verified by taking a damp blue litmus paper to test the identity of the gas. So when HCl is formed, it will be dissociate in the presence of water on the litmus paper to form H+ and turn the litmus paper from blue to red. PBr5 is actually available. However, it is not used frequently because it is quite corrosive and it decomposes above 100 degrees Celsius. And PI5 is almost non-existent as it quickly decomposes. Other methods include using thionyl chloride, SOCl2, at room temperature. So it can also react with alcohol at room temperature to produce a chloroalkane. SO2 and HCl are also produced. However, because these gases are toxic, so care has to be taken. Yep. So this is the example of the reaction that is occurring. Okay, so the OH is substituted by the Cl and SO2, HCl are formed as the byproducts. An anhydrous condition must also be used here because SOCl2 can also react with water. This reaction is sometimes preferred than PCl3 or PCl5 because the other two products of the reaction can be easily separated from the reaction mixture. Just that we need to take note of the safety aspects. So it must be carried out in a fume hood to remove the gases. Okay. A base is sometimes added to the reaction mixture to react with and absorb the HCl through neutralization reaction. SOBr2 is also available, but it is less stable and less widely used than SOCl2. So this is a summary of the methods to prepare each type of halogen alkanes, showing the best method for each halogen alkanes. So for RCl, this will be the best one. The one in bold are the recommended methods. As for RBr, we have this, and Ri, we have red phosphorus with iodine. All right. Now, let's examine the reactions of halogen alkanes. The carbon-halogen bond in the halogen alkane is polar because the halogen atom is more electronegative than the carbon atom. So the carbon atom bearing the halogen atom acquires a partial positive charge and is said to be electron deficient. This electron deficient carbon atom is open to attack by nucleophile. Nucleophile are species that are attracted to nucleus or positive charges. So nucleophile is a species that's able to donate an electron pair to an electron deficient atom in order to form a covalent bond. One characteristics of the reactions would be nucleophilic substitution with the other elimination. So this is a general flowchart to summarize what nucleophilic substitution is as well as elimination. Okay, we shall go into the detail of nucleophilic substitution. So the general form of nucleophilic substitution involving halogen alkanes is shown here. The halogen alkane molecule have the electron deficient carbon atom. So when the nucleophile is added upon heating, the nucleophile attached to the alpha carbon with the leaving group as the halogen. Nucleophiles are electron pair donor. If you observe closely, they are attracted to electron deficient sites. So they contain either at least a lone pair of electrons or a pi bond, but they may not be necessarily charged like ammonia and even water. So we have neutral nucleophiles where it has a lone pair of electrons or a pi bond, or we have anionic nucleophile which are charged like this shown. A leaving group is an atom or a group of atoms that is replaced by the nucleophile and departs during the substitution reaction. The leaving group can be charged or uncharged, but when it leaves with the pair of electrons that is originally bonded to the remainder of the molecule like here. So it brings the two electrons away, not just one, but both from the original covalent bond it is in. So the examples of neutral leaving group includes water or anionic leaving group like the halide. There are two mechanisms where nucleophilic substitution can happen. One is SN2, one is SN1. So whether a reaction proceeds by SN2 or SN1 mechanism depends on whether the reactant is primary, secondary, or tertiary halogenal alkanes. Now, consider the hydrolysis of bromoalkanes in hot aqueous sodium hydroxide. So this mechanism is nucleophilic substitution. But the examples show different mechanisms where nucleophilic substitution occurs. So this is bromoethane, which undergoes nucleophilic substitution with hydroxide ion. So hydroxide here is the nucleophile. And upon heating, the nucleophile substituted the bromine and the bromide leave as the leaving group. So this mechanism is SN2, okay, which I will elaborate. How do you see that the mechanism is SN2 or is SN1? As for this, the OH minus also substituted the bromine with the bromine as the leaving group. So the first one here refers to primary halogenal alkanes. So for primary halogenal alkanes, SN2 mechanism is preferred. For secondary halogenal alkanes, it can be either SN2 or SN1. For tertiary halogenal alkanes, where they have quite a lot of steric hindrance here, it will be SN1 mechanism. So what is the difference between them? Starting with SN2, consider the reaction between 2-bromobutane. All right, and aqueous sodium hydroxide that is hot. Okay, this reaction can proceed via the SN2 mechanism where it is a bimolecular nucleophilic substitution. So this mechanism is designated SN2 where S stands for substitution, N nucleophilic, and 2 means two reactant particles involved the rate determining step. So 2 reactant particles means it's bimolecular. So in general, we have the description of the mechanism as such. So the nucleophile is attracted to the alpha carbon, which is positively charged partially. And there is a transition state where the bromine is still attached to the carbon, but the bonds is weakening. So while the OH is attaching itself to the carbon, at the same time, the Br is slowly detaching itself from the molecule. So for nucleophilic attack, let's start with the first mechanism step. In a 2-bromobutane molecule, the CBr bond is polar, with the C carbon acquiring a partial positive charge because it is less electronegative. During the reaction, the OH minus nucleophile attack the partially positive charged C atom from the side directly opposite the Br atom. This is what we call a backside attack. Why must the nucleophile attack from the backside? Because the bromine block approach of the nucleophile is at the front. So because the bromine is leaving from the front, it's blocking the nucleophile from the front. That's why the nucleophile has no choice but to attack from the back. The nucleophile has to avoid the bromine because both are electron rich and will repel each other. Okay? In the transition state, the reaction is a concerted reaction taking place in a single step with both bond breaking and bond making occurring simultaneously. The nucleophilic attack leads to the formation of a transition state where there is a simultaneous partial formation of the CO bond and the partial cleavage of the CBr bond. Note that the transition state or the activated complex cannot be isolated. Okay? For the product, eventually the CBr bond break completely and the CO bond form to form Br minus ion and the alcohol as the products. Note that in this case, the partial positive carbon atom is also a chiral carbon with 4 different groups bonded to it. Note also that during the reaction, the 3 bonds associated with the carbon atom turn inside out. So there is actually a stereochemical inversion of the tetrahedral arrangement of the bonds to the C carbon, at which substitution occurs. So this reaction is said to have occurred with inversion of configuration with respect to the carbon atom, at which substitution occurs. So you can see that the CH3 is here, but when the product is formed, this CH3 is shifted to the other side, moved to more to the right. So that is what we call inversion of configuration. And the CH2 is also inverted to this side. All right. Because of the formation of the CO bond. Now, so in the reaction involving 2-bromobutane, the C atom at which substitution occurs is a chiral C carbon. Assume that the starting material for the reaction is a pure sample of one enantiomer of 2-bromobutane. So when the nucleophile attack from the back, it leads to an inversion of configuration. Experimentally, based on experimental results for sure, the SN2 reaction has been found to occur with complete inversion of configuration with respect to the chiral carbon at which substitution occurs. This is only possible if we have a backside attack during the reaction. It is impossible for the front to be attacked because based on the product form, if the nucleophile attack from the front, then there should be retention of the configuration, but this is not so. So based on experiment data and the reason given, like repulsion between a nucleophile and the bromine, it is impossible a frontside attack occur. This shows the energy profile of a SN2 reaction. The reaction is exothermic with the transition state having a higher energy level. And this is the kinetics of SN2 reaction, where rate equals to K, concentration of halogenal alkanes and nucleophile. The overall order of reaction is 1 + 1, 2. All right. Let's look at the factors affecting reactivity of halogenal alkanes, starting with the strength of carbon-halogen bond. SN2, which is bimolecular nucleophilic substitution, is a reaction for halogenal alkanes which involve the heterolytic fission of the CX bond. Studies have shown that the weaker the CX bond, the faster the rate of reaction. The order of reactivity of halogenal alkanes towards SN2 reaction depends on the strength of CX bond and increases in the order. RF, no reaction. RCl has the slowest rate of SN2 reaction, followed by RBr and then Ri, which is the fastest because the bond strength is the weakest. CF bond is too strong to be broken under normal lag condition. It can be broken, but it needs to be carried out at extreme conditions. So fluoroethane does not undergo hydrolysis even with prolonged heating under reflux with sodium hydroxide solution. The above order of reactivity of Rx towards SN2 reactions arises because the strength of CX bond decreases, as mentioned. Okay, so this is the relevant data quoted from the data booklet for the various carbon-halogen bonds. Why does the bond strength decreases down group 17? Down group 17, the size of halogen atom increases and the valence atomic orbitals of halogen atom X become bigger and more diffuse. As such, the overlap of orbitals which form the CX bond become less effective down the group. The strength of CX bond decreases down the group. In addition, the electronegativity value of the halogen atom X decreases down the group. This causes the polarity of the CX bond and the ionic character of the CX bond to decrease down the group. Consequently, the strength of CX bond decreases down the group. So these are the two factors that explain why there's a decrease in bond strength. And this is the electronegativity data. So we have both the increased size of halogen atom leading to less effective overlapping of orbitals, as well as the decreased electronegativity of the halogen atom down the group, leading to decreased ionic character. and decreased polarity. CCl bond is more polar than CBr because Cl atom is more electronegative than Br. This implies that the C atom in CCl bond has a larger partial positive charge and should attract nucleophiles more strongly than the C atom. However, despite having a more electron deficient carbon to attract nucleophiles, RCl is found to undergo SN2 reactions at a slower rate. The order of reactivity of halogen alkanes towards SN2 reactions does not depend on the magnitude of the partial positive charge on the carbon on the CX bond. Now, steric effect of R groups in SN2 reactions. Studies carried out indicate there are large differences in the rate at which the various classes of halogenal alkanes, methyl primary, secondary, or tertiary, undergo nucleophilic substitution by the SN2 mechanism. These differences in the rate reflect the steric hindrance each class of halogenal alkanes offer to nucleophilic attack. During the SN2 reaction, the nucleophile must approach the halogenal alkane molecule and attack the electron deficient carbon atom from the side directly opposite the halogen atom, known as a backside attack. And this approach and attack is hindered by alkyne substituents bonded to the carbon atom that's been attacked. In general, the SN2 mechanism is favored by less steric hindrance around the carbon atom bonded to the halogen atom. The order of reactivity of halogenal alkanes with the same halogen atom X towards the SN2 reaction decreases in this order. So we have CH3X having the least steric interference or hindrance, and the tertiary halogenal alkanes having the greatest steric interference. So with less steric interference, SN2 mechanism is more favored, most reactive, and less reactive here. So for primary halogenal alkanes, the attack will be easy. For secondary, the attack is possible, but for tertiary, impossible because of too much steric hindrance. Now, let's move on to SN1. So SN1 is denoted by this. This is the only difference between SN2. We have only one reactant molecule or unimolecular reaction in the rate determining step. So in SN1 mechanism, the main focus is on the formation of the carbocation. In step 1, the CBr bond undergoes heterolytic fission. Means opposite of homolytic, means uneven cleavage, which means the electrons in the covalent bond are taken away by bromine. So it is considered heterolytic fission. The carbocation intermediate was formed. So this is the rate determining step because it is slower as it involves bond breaking that is endothermic. So energy is needed for the reaction to proceed. The carbocation form is trigonal planar with respect to the positively charged carbon atom. And this is sp3 hybridized here, but the positively charged carbon is sp2. This is sp3, this is sp2 hybridized. So in step 2, we have the nucleophilic attack on the carbocation. So after the carbocation is formed, the nucleophile will start to attack the carbon. So in step 2, the hydroxide nucleophile will attack the positively charged carbon atom of the carbocation from both the right or the left side with equal likelihood because there is no blockage on both sides. So this will yield equal amount of a pair of enantiomers as products, which is known as a racemic mixture. So in this case, SN1 reaction proceed with racemization with a single chiral carbon center. Racemization involves the formation of equal amount of two enantiomeric products from a single starting material. So we have a pair of N enantiomers with one having inversion or configuration and the other retention of configuration. In the reaction involving 2-bromobutane, the carbon atom at which substitution occurs is a chiral C carbon. Assume that the starting material for the reaction is a pure sample of one enantiomer of 2-bromobutane. So this is a pure sample of one enantiomer of 2-bromobutane, which is optically active because of the chiral carbon. So in SN1 mechanism, we expect to see two enantiomers of equal amount because of equal likelihood. One have the configuration inverted, the other retained. From the mixture of products obtained, the SN1 reaction is said to occur with racemization. The substitution reaction takes place with 50% of the product molecule showing retention of configuration about the chiral carbon atom, while the other 50% show inversion of the configuration. And the reaction that transforms something that's optically active compound to racemic mixture is said to be racemization. And this is the energy profile that looks different from SN2. SN2, we only have one P, one activation energy. But in SN1, we have two steps involving the formation of the carboxyl ion in the first step, and then the reaction of the carboxyl ion with the nucleophile. So there are two activation energy. The kinetics of SN1 is just rate equals to K times concentration of the halogenous alkane, which is the rate determining step. So the overall order of reaction is just 1, not 2. What are the factors that affect the reactivity of halogenous alkanes in SN1 reaction? So the rate determining step of SN1 reaction involves the cleavage of the CX bond in the molecule. So the weaker the bond, the faster the rate. So it's quite similar to SN2, where the weaker the bond, the faster the rate. So you can study them as a whole, okay? The order of reactivity of halogen alkanes towards SN1 reaction depends on the strength of CX bond and increases in this order, with RF having no reaction because the CF bond is too strong to be broken under normal lab conditions. So, but there's another factor that is not in SN2, is in SN1 because of carboxyl ion, which is the stability of the carboxyl ion. The rate of SN1 reaction depends on the rate of formation of carboxyl ion via the heterolysis of CX bond. The rate of SN1 reaction increases as the stability of the carboxyl ion increases. This is because a more stable carboxyl ion is formed faster due to a lower activation energy needed for its formation. In general, SN1 mechanism is favored by factors that stabilizes the carboxyl ion. So we have electron donating groups like the alkyne groups, which helps to stabilize the carboxyl ion by dispersing the positive charge of the carbon atom. As such, the stability of the carboxyl ion increases as the number of alkyne groups, which is the electron donating group, increases. The order of reactivity of halogenous alkanes toward SN1 reactions increase in this order. So we have the most substituted halogenous alkanes, the tertiary one having the higher reactivity, and the methyl one without any methyl group bonded to the alpha carbon having the least reactive. So this table summarizes the difference between SN1 and SN2. You can just read yourself. In SN1, the focus is on the carboxyl ion stability. SN2 is on the steric interference. Now, when we know this reaction mechanism is SN2 or SN1. So at A level, for simplicity, we just need to consider the structure of the halogenous alkane, okay, for the syllabus purpose. So if we have a methyl halogen, okay, then it is SN2, all right? If it's primary halogenous alkanes, it's also SN2. But if it's secondary, it can be either SN2 or SN1. Then for tertiary halogenous alkane, because of the steric interference, we will have SN1. So for these two, right, the reason why they are SN2 is because there is less steric hindrance for backside attack. Okay, so imagine if we have more steric interference, it will be very hard for the nucleophile to attack from the back. And also, it doesn't lead to the formation of a stable cation. So it can be SN1 mechanism. As for the secondary, we will need more information like kinetics data, optical activity data to determine whether this reaction can be SN1 or SN2. As for tertiary halogenous alkane, is clear-cut SN1 because of the formation of more stable cation due to the electron donating groups bonded to the carbon. And also, there is more steric hindrance for backside attack. So SN2 cannot occur. Carbocation more stable, so it's SN1. However, there are some special cases you just take note, the exceptional cases. So actually, there are some primary halogenous alkanes that undergo substitution reaction via SN1 and not SN2. So let's look at the special case. We have 3-bromopropene, all right, reacting with hydroxide from the sodium hydroxide and heating, all right. Now, this mechanism is not SN2, it's SN1, although the halogenous alkenes here is not, it's actually primary. So by right, it's SN2, right? But no. What is the explanation? So 3-bromopropene, right, can undergo nucleophilic substitution via SN1 because it actually can form stable carbocation. Yes. In this case, it forms a carbocation where the positively charged carbon is adjacent to the double bond. So in this carbocation form, what happens is that the empty p orbital of the positively charged carbon overlap with the pi electron cloud of the adjacent carbon-carbon double bond. This allows the pi electrons and the CC double bond to delocalize over the positively charged carbon and disperse the positive charge, and thus stabilizing the carbocation. Another explanation is that these 3-bromopropene form a carbocation that is resonance stabilized due to the presence of the carbon-carbon double bond. So the carbon-carbon double bond will allow for resonance structure to be formed like this. Another special case will be the hydrolysis of benzene or benzyl bromide. So this is benzyl bromide. You would think that it could be SN2 because this carbon is bonded to 2H. No, it's SN1 also. Now, what is the reason? So benzyl bromide can undergo SN1 mechanism because it also forms a relatively stable carbocation. So in this case, it forms a benzyl carbocation in which the positively charged carbon is adjacent to the benzene ring. So in this carbocation, the empty p orbital of the positively charged carbon overlap with the pi electron cloud of the benzene ring. So this allows the pi electrons of the benzene ring to delocalize over the positively charged carbon and disperse the positive charge. And this stabilizes the carbocation. An alternative explanation would be the benzyl bromide forms the resonance stabilized structure due to the presence of the benzene ring. Okay, so this is the resonance structure of the benzyl bromide. So these are examples of nucleophilic substitution reactions of halogenal alkanes. So far we have covered the general characteristics of SN1 versus SN2, but we haven't gone into the specific reactions. So this is a summary of what is going to happen in the next few lessons. The bromoethane undergoes various nucleophilic substitutions with these reagents to form the compounds. All right. Now, starting with the formation of alcohol. So these nucleophilic substitution reactions of halogenal alkanes with aqueous sodium hydroxide is commonly termed as hydrolysis or alkaline hydrolysis. So the reagent involved will be sodium hydroxide or potassium hydroxide and heating. Aqueous medium must be used to ensure that nucleophilic substitution occurs. So the state symbol of sodium hydroxide must be stated explicitly. Should alcoholic medium be used, elimination reaction will be taking place preferentially. So this is the example of bromoethane hydrolysis by sodium hydroxide. And because we are talking about primary halogenal alkanes, SN2 reaction occurs. So SN2 means backside attack by the nucleophile, forming the transition state. Yeah, this is the mechanism. So it's similar to what we have done. So we're going to go through this quite quickly. Another example, we have this, which is actually tertiary halogenal alkanes undergo SN1, unimolecular nucleophilic substitution. So the mechanism looks different. So we have the formation of carbocation first, and then we have the Br as the leaving group, and then the nucleophile attack the positive carbon to form the product, which is the first step here. Now, formation of nitriles, RC triple bond N. This nucleophilic substitution reaction of halogenal alkanes with potassium cyanide in aqueous ethanol is useful to synthesize organic compounds because it is a method of increasing the length of carbon chain by one more carbon. So if you want to increase the length of the carbon chain, we use this. And this reaction is an example of a step-up reaction because the number of carbon atoms in the product molecule is one more than the reactant molecule. So we have this reaction, Rx plus KCm with ethanoic KCm and heat to form nitrile and KX. So these are the reagents and conditions. So in practice, a mixed solvent is used for the reaction to improve the miscibility of the reactants. So in this case, KCm dissolve in water, whereas Rx dissolve in ethanol. Example of reaction between bromoethane with ethanolic KCm. So we have this, and this is still SN2 reaction, backside attack, transition state, product. So we form a nitrile because of the cyanide line. All right. Cyanide look like this. Okay. Cyanide ions. Now, so cyanide is the nucleophile. Okay. So it's 1, 2, 3, 4, 5. Yeah, 6. We have the lone pair of electrons on the carbon that attack the alpha carbon in the molecule. All right. Next, we have nitriles are useful intermediate compound in synthesis. They can actually be further reduced to a primary amine or be hydrolyzed to become carboxylic acid or carboxylate salt. So for reductions of nitriles to primary amine, we have this. So the nitriles react with hydrogen, which is reduction. Addition of hydrogen is reduction. Of course, catalyst of nickel is needed. So it's actually hydrogenation, right? It forms a primary amine. So what happened is that the structure is extended lah. Okay, so the triple bond is broken and the nitrogen form bonds with the hydrogen added to it lah. The carbon also added with the hydrogen. So 4 hydrogen atoms, 2 of them bonded to C, the other 2 bonded to N to form the primary amine. And then other than this reagent and condition, we can also use lithium hydrogen hydride, LiAlH4, in dry ether as a solvent to produce the same product. The nitriles that is formed from here can also be further hydrolyzed to carboxylic acid using acid or base hydrolysis. So if we use acid hydrolysis, carboxylic acid is formed where CN becomes COOH and the M come out to form NH4 plus. In a base hydrolysis, we also form COO minus, but the H, right? Form the NH3. So the N come out, form this 2H. So there's no H attached to the RCN for the base hydrolysis, unlike the acid hydrolysis. All right. Okay. Now, other methods to produce the primary amine include the reactions of halogenal alkanes with concentrated ammonia in ethanol. So this is another way of producing the primary amine. Just that the conditions is very specific: excess concentrated ammonia in alcohol and sealed tube heated. Other possible equations include this, where we form a primary amine salt. Okay, possible, right? And the primary amine salt, right, can further react with sodium hydroxide to liberate the free amine. So again, you can take out the X to form the primary amine and form sodium X and water. Or it can form it's the same one as here actually. But then instead of using sodium hydroxide, right, we can add excess ammonia to form the primary amine. So the reaction mixture will contain primary amine salt here, and the ammonium salt. Or that's it. Also, this will do. Okay. Now, so basically is to remove the X from the halogenal alkane. One example here we're going to emphasize is the reaction of bromoethane with ammonia. So when bromoethane reacts with ammonia in the presence of excess concentrated ammonia in alcohol, sealed tube heat, we can form ethylamine. And the mechanism is definitely SN2 with the backside attacked by the nucleophile NH3 transition state product. And there's a inversion of configuration about the carbon. Now, from here, when we add because the ammonia is in excess, so the ammonia that remains will continue to react with the product here. So what happens is that there's a proton transfer reaction. Okay, so the H from here is transferred to ammonia to form the ammonium salt. And a primary amine is formed. All right, so take note that for the transition state here, there's conservation of charge. The transition state actually has a net charge of 0 because both reactants are uncharged. Now, however, we need to understand that there could be a problem encountered with this method of preparation of amine, as the mixture of product is obtained due to polyalkylation. So once we form the primary amine, what happens is that it can undergo further reaction, okay, and go on and on again. So what happened is that it can continue to react, right, with the bromoethane continuously, as long as there's sufficient amount of this. All right. So since the primary amine form is also nucleophilic, it can also undergo further reaction, giving the secondary amine here. Okay, so if you look at the mechanism, right? So normally when we draw the arrow and mechanism is from the electrons towards the positive. So this is like this. And then when this attract this will go this. One attract here, the other have to go the other way. And then you form this. And then this one react with excess ammonia to form NH2. So it's a proton transfer according to the previous page. So the H transferred to this one in a reversible reaction. And then the NH2 again, this is a lone pair of electron attack, give up, leaving group, form this. All right, because these two come together already, right? So you extend the carbon chain. And then with proton transfer again, NH. So by similar equilibrium and further alkylation means you keep on adding the methyl group. The tertiary amine and even the quaternary ammonium compound may be formed if you allow the reaction to proceed. So the actual result will be a complex mixture of products. On an industrial scale, the products are separated by the addition of alkaline to liberate the free amine, followed by fractional distillation. So to avoid this situation, we use excess ammonia to minimize polyalkylation. So if let's say the intended product is this, then we use this. But if the intended product is the quaternary ammonium salt, right, then we use excess of the bromoethane. So it depends on what you want in the end. So this method, right, is limited to the formation of aliphatic amines because array halides, right, will not undergo nucleophilic substitution with ammonia. They won't react. So it only affects the aliphatic ones. Next, formation of ether from alkoxide ions. Halogenal alkanes can undergo nucleophilic substitution with alkoxides to yield ether. Okay, so this is the Williamson ether synthesis reaction. So we have the halogenal alkane with the alkoxides means you have O minus Na plus. Yep. Not H, but it's like a salt like that lah. Then it will form the ether. So what happens is that the R join to the O. So this thing come off. The X join to the Na. This one join to the other. So you can ROR dash. Okay. And these are the reagents and conditions. The sodium alkoxide is prepared by reacting sodium with appropriate alcohol. So we add sodium to methanol to produce sodium methoxide. So in the above acid-metal reaction, methanol acts as an acid. And the reaction between the alkoxide and the bromoethane is something like this, which is SN2 again. Okay, we shall not elaborate on this to form the ether. Yeah. So if you use CH3O minus, it's a negatively charged nucleophile. CH3OH itself is a neutral nucleophile. Both are nucleophile. Formation of ether from alcohol. So after the ether was formed, it can undergo further reaction. Yeah. So we have bromoethane with the alcohol to form the protonated ether. All right. And then the protonated ether reacts with more methanol to form the ether. So this is the mechanism of the reaction, which is SN2 again. Okay. Okay, just take a look at this before we progress to the next session. So after the protonated methoxide ether, ethane is formed, it undergoes further reaction with alcohol. So this is just one step, no? So after this is done, there's a second step. Yeah. So we can either form ether through this with alkoxide ions and the halogenal alkane, or you take the alcohol with the halogenal alkane, but then it will take two steps lah, as shown. Yeah. So this nucleophile attack, give out. This attack here, you take away this hydrogen. You see that? So you attack this, then this one give out back to oxygen. So you have CH3O, the H gone already, H go to this side already. So here become back the CH3OH, OH2. Yeah. It's it form back this thing. Okay. Let's move on to the last section on elimination reactions of halogenal alkane. Elimination reaction involve loss of element from the starting material to form a new pi bond in the product. Halogenal alkanes can undergo elimination reactions when heated with alkali in the presence of alcohol as the solvent. So this is a general equation that shows elimination. We have the alkane reacting with hydroxide. Condition will be alcoholic KOH, of course, plus heating to form the alkene and water and the halide ion form. So these are the reagents and conditions. So in this case, right, alcoholic KOH must be used and not aqueous because the OH minus in alcoholic medium behave better as a base than as a nucleophile. So during the reaction, the elements of HX are lost and the alkene is formed. This reaction is known as dehydrohalogenation, since both H and X are eliminated from the halogenal alkanes. The elimination of elements in HX is possible for halogenal alkane only if the halogenal alkane molecule contains a beta proton, which can be lost during the elimination reaction. What is beta proton? So alpha carbon is the carbon bonded to the functional group. In this case, will be X. So this is alpha carbon. Beta carbon is the carbon adjacent to the alpha carbon. And beta protons are the hydrogen atoms attached to the beta carbon, which is this one. The one I circled in red. So how is the mechanism look like? So we have the reaction of 2-bromo-2-methyl propane with hot alcohol KOH. So this is the overall equation where the double bond is formed. Okay? There are different elimination mechanisms. The mechanism for the above reaction is E2, but it's not in the A-level syllabus. But we will just go through it for learning purpose. Okay? So what happened here is that the base OH minus, so in alcoholic medium, it behaves as a base. The base OH minus will start to remove the proton from the beta carbon, forming H2O. Okay? The electron pair in the beta CH bond forms the new pi bond, the double bond. So when the H is removed, right, this bond come down here, it forms a new pi bond. Okay? At the same time, the CBr bond undergoes heterolytic fission. So there is a cleavage of bonds here. So this Br minus is the leaving group that remove the electron pair in the CBr. Okay? So this is the E2 mechanism, elimination. So this is the drawing of the mechanism. The lone pair of electron attack this H to remove the H, and this one come back here, and this one lost. And you form water and HS minus as the byproduct. So looking at the reaction of 2-bromobutane with hot alcohol KOH. Okay, we form but1-ene as well as cis-but2-ene and trans-but2-ene. Okay. Why is it so? The trans product is favored due to steric factor. There is less repulsion of the methyl groups in the trans-but2-ene. Here, there is a lot of steric hindrance. So this trans product is a more stable product lah. Okay. Why is it build one? Because it depends on, it can be here or here lah. So it can be build one or build two in lah. Now, Zef or Zetsif rule states that for elimination reactions of alcohol of halogenal alkanes to alkenes, the preferred alkene is the alkene with the most alkyne groups attached to the doubly bond carbon atoms, which is the most highly substituted alkene. The reactivity of halogenal alkanes towards elimination reactions depends on the strength of CX bond and increases in the order. So again, this one, no reaction because of the strength of the carbon halogen bond. For this will be the strongest, sorry, will be the fastest because of the weakest bond. Now, many nucleophile actually can be acting as base. Hence, nucleophilic substitution reaction involving halogenal alkanes are accompanied by elimination reactions. A mixture of product will be obtained. However, by choosing the suitable conditions such as appropriate nucleophile, temperature, and solvent, we can optimize the production of the desired product. So for simplicity, when we use aqueous sodium hydroxide, it is SN2 mechanism, nucleophilic substitution. If it's alcoholic, it will be elimination, but that is for simplicity lah. Okay. Lastly, we go to halogenal arenes, which are halogen derivative of arenes in which one or more hydrogen atoms of the benzene ring in the arene molecule is replaced by a halogen atom. The molecules of halogenal arenes contain one or more halogen atoms bonded directly attached to the benzene ring, and each halogen atom is sp2 hybridized carbon. Now, halogenal arenes are also known as arene halides and are represented as ARX, where AR represents arene groups. And these are the nomenclature when we name arenes: fluorobenzene, 2,4-dichloro-1-methylbenzene, alphabetical order. And we have this one, 1-bromo, 3-chloro, 2-fluoro benzene, alphabetical order in the naming as well. As for physical properties, halogenal arenes burns with a sooty, luminous flame, which is characteristics of unsaturated compounds containing benzene ring, because it has a higher percentage of carbon, leading to more incomplete combustion. And the halogenal arenes are colorless liquids, which are insoluble in water, but denser than water. Chlorobenzene and bromobenzene can be prepared from electrophilic substitution reactions of benzene with halogens in the presence of a suitable catalyst, which we should not elaborate here. If you want, I can prepare a video on chemistry of arenes and benzenes, where we talk about electrophilic substitution in detail, how the mechanism occurs. Okay, what are the things to take note? Halogenal arenes are significantly less reactive towards nucleophilic substitution than the halogen alkanes, but they still can react in nucleophilic substitution like this. Okay, but if you talk about chloroarenes, it's like almost no reaction. So we just treat it like no reaction lah. Okay. Why are they not reactive? It has to do with the partial double bond character in the carbon halogen bond. So in the halogen arene molecule, the p orbital of the halogen atom overlap with the pi electron cloud of the benzene ring. This allows the lone pair of electrons in the pi orbital of the halogen atom to delocalize into the benzene ring, which result in a partial double bond character in the carbon halogen CX bond. The bond is thus strengthened and not easily broken because of the good overlapping between the pi electron cloud of the benzene ring and the p orbital of the halogen atom, as shown here. So the p orbital electrons can be delocalized and strengthen the bond. Also, there is steric hindrance and electronic repulsion due to the benzene ring. The halogenal arene cannot react via SN2 because SN2 requires attack by the nucleophile backside, right? Backside attack. So nucleophilic attack at the electron deficient carbon atom from the side opposite the halogen atom is blocked by the benzene ring. The pi electron club is also repelling the nucleophile. The halogen arene also cannot react via SN1 because it cannot form a stable carbocation. Yeah, so you cannot stabilize a carbocation with a benzene. So they are not reactive towards nucleophilic substitution. Under normal lab conditions, the carbon-halogen bond in the halogenal arene does not break and no nucleophilic substitution reactions occurs. However, under more severe industrial conditions, we do have reactions involving them. That's what I said just now. But in normal lab conditions, no. It has to be done under extreme conditions. One example is the synthesis of phenol from halogenal arenes under high pressure and high temperature stated here. Now, so you can actually force it, okay, to happen, but it has to be at high pressure and temperature. Okay. Another example is this one, sodium phenoxide, where you can actually remove the Na and form the phenol. Yeah. Oh, I'm sorry, I'm saying these are two steps, sorry. So you have chlorobenzene reacts with sodium hydroxide. So sodium substituted the chlorine, all right, with the O. So it's ONA substituted the chlorine to form the sodium phenoxide. Okay, ONA. Then after that, okay, after that, right, this sodium phenoxide react with HCl to form back the phenol. So it actually neutralizes lah. Okay. Halogenal arenes such as chlorobenzene or bromobenzene undergoes electrophilic substitution reactions because of the benzene ring, which we learned in the previous lesson. I will do it next time on the chemistry of benzene next time. Like nitration, halogenation, or Friedel-Crafts alkylation. Okay. So halogenal arenes actually react less readily than benzene in electrophilic substitution reactions. The reason is because when you form the halogenal arenes, right, the halogen substituent is electronegative and electron withdrawing. So it decreases the energy density in the benzene ring and make the benzene ring less able to attract electrophile. It's therefore a deactivating group because it reduces the reactivity of the benzene ring towards electrophilic substitution. Also, halogenal arenes yield a mixture of products in electrophilic substitution. The reason is the halogen substituent is a 2,4 directing group. So it will direct the incoming electrophile to attack 2 and 4 position. So it will result in formation of a mixture of 2 major organic products. So what are the distinguished tests? We use sodium hydroxide, dilute nitric acid, and silver nitrate via the 4-step test. So how do you distinguish between RCl, RBr, and Ri? Number one, we can heat each sample using sodium hydroxide in a test tube. So there will be hydrolysis and the CX bond will break to produce an X minus. And then we can cool the mixture. The cooling is important to prevent the thermal decomposition of the silver nitrate, which will be added in the step 4. After that, in step 3, we acidify the mixture with dilute nitric acid. This will help to remove any excess sodium hydroxide added in the first step. Because if there is sodium hydroxide remaining, all right, then it will react with silver nitrate added in the step 4 to form a brown precipitate. Then it will be difficult to observe the color of the precipitate formed from the desired product. We can't use hydrochloric acid or sulfuric acid because they will actually react with silver nitrate to form silver chloride and silver sulfate, which appear as white precipitate. So in the last step, we add silver nitrate and the precipitate of the silver halide will be formed. So there are 4 steps involved, and there is a reason for each step to be carried out in that order. So if it is chloroalkane, we will observe white PPT. If it's bromoalkane, it's cream or pale yellow PPT or silver bromide. If iodoalkane, will be yellow PPT or silver iodide. To distinguish between chloroethane and chlorobenzene, what is the chemical test? We can add sodium hydroxide to each sample and heat the mixture. And then we cool them down and acidify with dilute nitric acid and add silver nitrate. So if the unknown is chloroethane, we will observe silver chloride. If it's chlorobenzene, no precipitate form. Okay? Because chlorobenzene will not react with sodium hydroxide, but there's no nucleophilic substitution. We went through that before, right? Yep, here. Okay, and then okay, the next one. To distinguish between halogenal alkanes and other functional group like 1-chlorobutane with butane 1-nol. So we can add sodium hydroxide and heat each mixture, cool, acidify, and add silver nitrate. If it's chlorobutane, white PPT. Butane 1-nol, no PPT. All right. How about differentiate between 1-chlorobutane and butane 1-nol? Other ways. So another way is to use ethanolic silver nitrate and warm each mixture. So in this case, right, for the chlorobutane, okay, we will see a white precipitate observed. All right. So you can either use this method or just use silver nitrate ethanoate instead of sodium hydroxide and then acidify. Very troublesome. So this is actually faster than this one. Less steps involved. The observation will be similar. And the equations to represent the reactions will be as such. So if it's chlorobutane, it will react with nucleophile, forming a protonated ether. And then the protonated ether, right, will further react with more ethanol to form the ether. So there's no precipitate form here. There's precipitate form here, sorry. Then the chloride form will react with silver to form silver chloride. All right. Now, due to the strength of CF and Cl bonds, fluoroalkanes and fluorochloroalkanes are stable molecular entities under stable ambient conditions, exhibiting low toxicity, low reactivity, and low flammability. So of all the fluorohalogenal alkanes, CFC manufactured under the trade name freons are most widely used. So CFC are halogenal alkanes that contain only chlorine, fluorine, and carbon. Their molecules contain only CF and CCl bonds and no CH bond. They are sold under the trade name of freons. Examples are CFCl3, CCl2F2, and C2Cl2F4. Now, since CF and CCl bonds are relatively strong, CFC are relatively stable under normal atmospheric condition. Of course, in the presence of nucleophile, CFC containing CCl bonds are reactive. CFC have some desirable properties which makes them useful compounds for various applications. So these are the examples for your own reading. Halogens are halogenal alkanes related to CFC that contain only carbon, bromine, and other halogens without hydrogen. So they are used in fire extinguisher system because they're effective fire retardants. The heat-induced cleavage of the weak CBr bond releases bromine atoms, which suppresses compression by inhibiting the free radical chain reactions occurring in flames. Since CFC and halogens can damage the ozone layer, their use has been discontinued. So the interim replacement are hydrochlorofluorocarbons, which deplete stratospheric ozone, but to a much lesser extent. Such compounds with CH bonds are destroyed at lower altitude before reaching the stratosphere. HFC will replace HCFC because they have ozone depletion potential. So the use of this substance in the table above, they act as greenhouse gases and may contribute, so they may be replaced in time to come. Now, what happened on the ozone layer? It is present 20 to 50 kilometers above the Earth's surface in the stratosphere. And you can read yourself here, but we are just focusing on the reactions. The oxygen molecules absorb UV radiation and dissociate into radicals. So the UV light break the covalent bond between oxygen atoms, and the radicals of oxygen attack another oxygen molecule to form ozone. Okay? And then this ozone is broken down to form O2 and ozone. And this ozone reacts with the radical to form by oxygen, and the process repeats itself. So they are actually in a dynamic equilibrium. It's a continuous process of reactants forming product forming back the reactants. Now, what is CFC doing to disrupt this equilibrium? So I will just jump to this part on what CFC is. Again, is stable, unreactive under normal conditions. So because of that, their stability allows them to remain for a long time. And then because CF bond is very strong as mentioned, but CCl bond is weak enough to be split up by the UV radiation to produce the chlorine radical. And this chlorine radical will start to react with the ozone molecules and disturb the balance equilibrium as you see just now. So what happened is that the chlorine radicals produced from CFC act as a homogeneous catalyst, which means is in the same state as the reactant. So the reactions are as follows. The CFC molecules absorb UV radiation, and the CCl bonds undergo homolytic fission with electrons on both sides equal in number. And then this chlorine radical will then combine with the ozone molecule to form ClO, chlorine monoxide, and oxygen form as well. The ClO then reacts with another radical to form Cl radical and oxygen. So this Cl radical is regenerated in step 3 and return back to step 2 to attack more ozone, to deplete the ozone. So the chain propagation step proceed continuously 2, 3, 2, 3, 2, 3. So a single chlorine radical can literally lead to the destruction of thousands of ozone molecules because of its ability to get regenerated in step 3 and return in step 2 to attack more ozone. So the net equation is just simply the ozone becoming O2. Yeah. When you combine step 2 and step 3 together, Cl is the catalyst in this case. So this part you can read yourself. And we are done. This is a summary of today's lecture, everything about the reactions of halogenal alkanes. Like the preparation is actually nucleophilic substitution or electrophilic addition or free radical substitution. And the reactions can be either elimination or nucleophilic substitution, whereas one of the product nitrile can be further reacted in reduction, acid hydrolysis, or base hydrolysis. We also talk about the difference between SN2 versus SN1 mechanism, know it very well, and the distinguishing test lah. Okay, so I hope it helped you to understand this topic on halogenal arenes and alkanes, halogen derivative. So that's it. Thank you.